We have Justin David talking about entanglement properties of the graviton.
Yeah, so thank the organizers for inviting me, yeah, maybe my talk was a little outside this community, but maybe because I'm not going to stay till the end, maybe I can just tell congratulations to Bal, and in fact, just some reminiscence. I met Bal, I think, first time when I was a student at Tata Institute, and he was talking about posets, I think, at that time. And the next time is sort of the time I met him at IOP. There was some meeting at IOP that time. All the communities were together, the string theory and the general field theory community. And that time, I think he spent some time with me in one of the rooms. And at that time, I was learning string perturbation theory. And he was listening to what I was learning. And he was giving me comments. And now when I go back and think about it, and he's a senior professor. I was just a second-year student or something. I can't imagine myself listening like that to somebody. And I thank for all that interactions, and we had times later on together interacting. And so I thank you, Val, and congratulations. So let me talk about entanglement properties of graviton. And this was work done with the student Jyoti Moy at ISC. And let me begin with a brief introduction. Entanglement is actually a difficult quantity to evaluate in quantum field theory. And evaluating it for theories with gauge symmetry, it's even more difficult, even if they are free. And the usual method has been the replica trick, which has been most successful in 2D CFTs. And as many of us here know, that entanglement entropy has played a crucial role in understanding holography as well as black hole physics. Now, in spite of that, in spite of the fact, entanglement has played a crucial role in gravity, there's been very little study of entanglement entropy of just gravitons. Okay. And in fact, one would need that for understanding formulas like these, which are sort of, I think this, like this, which occur, recently. It has been these such generalized entropy formulas have played a role in black hole information paradox, in which this quantity S bulk involves, partitioning the region into two regions, in which one includes entanglement entropy of gravitons also. So these are sufficient motivations to study entanglement properties of the gravitons. And in fact, graviton is a fundamental particle in nature, and it is a sort of just a natural thing to understand what its entanglement properties are. Now, what I will focus on is a restricted case, just linearized graviton, the linearized theory, and which admits a particular gauge symmetry. The simple question one can ask is that, what's the logarithmic, as in the previous talks, people have talked about the area of term in entropy, but in entanglement entropy. But when you partition a region into two parts, there are, especially in even dimensions, there is a logarithmic growth term. And and in fact, that is the sort of renormalization group invariant term. And what is the logarithmic coefficient of entanglement entropy of a spherical surface? You just partition it into a sphere and ask the question, what is the logarithmic coefficient of that entanglement entropy? So, for instance, for free scalars, this is the numbers, -1 by 90, 11 by 90, and Cassini and Huerta have evaluated it. And can one study these, for the graviton? Suppose there are excited, this is for the vacuum, suppose there are excited states, can one study entanglement of excited states involving graviton? So these are the very simple questions one is asking. Now, for theories with gauge symmetry, due to the Gauss law, the Hilbert space does not factorize into two subregions. I will detail it a little bit later again. And it actually factorizes as sum of superselection sectors. And there is a contribution of entanglement due to the sum. Now, for a theory with gravitons, how do you find the superselection sectors? How do you find the entanglement entropy of these sectors? Now, and the second question is, okay, you have the ground state, can you study excited states over it? So let's just begin with the definitions again, just simple. So we begin with a spatial region, spatial subregion in CFT. and we consider it at a time slice, divided into two regions, A and A bar. A is a sphere for us in all the cases, actually, except the last if I have time. And suppose the Hilbert space factorizes into two subparts. Then one reduces, evaluates the reduced density matrix by tracing over the complement region and takes the von Neumann entropy of that particular reduced density matrix. And that's your definition. And if you're dealing with spin systems, or a lattice system in which degrees of freedom are spins, then the Hilbert space does factorize. And theories, but and this trace can be carried out, and in principle you can evaluate the entanglement. So theories with gauge symmetry, including gravity, does not admit this simple factorization. The gauge invariant factor Hilbert space doesn't factorize, and let's see this for the Maxwell's theory. Yeah. Scalars? It does not. Like suppose it's just spin system. Okay. Yes.
No, finite dimensionally,
yes.
But the moment you go to quantum field theory,
yeah.
all the local algebras are
Yeah. So there is an ambiguity in definition of that local algebra. Yes, indeed. Yes. Yeah.
No.
For even scalars. Yeah, I understand that.
No,
yeah.
whatever it is universal. Type 3.1 is the characteristic property of
yeah.
all local quantum field theories, apparently also related to gauge theories. And
Yeah.
there is a general theorem that you cannot factorize, you cannot localize these algebras in terms of states.
Yes.
So the, what is it, bond rule does not apply.
Yeah. Yeah, okay, I
By the way,
understand for the
let me make
scalars,
a
but so when you have, that leads to an ambiguity on defining sort of the edge modes.
No,
Yeah.
no, that's not correct. So
That's not clear.
There is a old
Yeah.
result due to Fermi.
Fermi,
That
okay.
if you assume factorization, it
Yeah.
leads to causality violations. Okay, and it was resolved only let's say 10, 12 years ago, because of the assumption of factorization of bond rule. For this is something to do with electromagnetism.
This is for electromagnetism.
Yeah. The problem you are dealing with is that there is a split property.
Split property, yeah.
For space-time localized algebras, and the split algebra, the splitting thing is type 1. So that does admit density matrices, which can be restricted to type 1 has trace class operators. You can so then you get a mixed state a priori. And I saw a paper today from Kumar Gupta that Roberto Longo and a colleague of his have proved, I don't know how they did it, that even in this case, they can find a finite entropy.
Yeah.
This I don't know how they did.
So here, of course, I mean, when you talk about gauge symmetries, I mean, because of the Gauss law, there is no fact. That's the simplest thing I'm talking about.
Yeah,
the
I
Gauss
understand.
law. Yeah.
But the theorems that they are quoting seems to be completely general. It seems to have very little to do with the kind of quantum field theory you're dealing with locally.
Right.
Gauss
But
law,
then, okay, so, yeah, so, okay, let me just go ahead and then we will come back and let's see what, So let's go ahead with this Gauss law, I mean, for the Maxwell's theory and what I mean. I mean, I'm meaning factorizability in a very restricted sense only. So due to the fact that the Gauss law must satisfy, I mean, states must satisfy the Gauss law, the Hilbert space actually breaks down into this form. So there is this sum over the electric sectors. I will sort of detail this later. And the Hilbert space, inside and outside Hilbert spaces run over the sectors actually. So so the Gauss law actually requires the radial electric field to be identical inside and outside. So let me just go to the explicitly. Here is some picture. And this is the radial electric field, and the electric field configurations should be matched inside and outside. And just to see that explicitly, we choose a gauge. So we are like in Maxwell's theory, we choose a gauge, and the states satisfy this property, the Gauss law property. And this, of course, by everybody's argument, the pillbox argument leads to the fact that inside and outside electric field should be matched. And gauge invariant operators, suppose you built Hilbert spaces inside, the gauge invariant created by Wilson loops, little Wilson loops, cannot change this electric field configurations. So, and the Gauss law links the inside and outside. So, therefore, just choosing a region, the Hilbert spaces actually, the Hilbert space breaks down into this particular form. It tensor products, but sum over the electric field configurations. So then how do you define the entanglement for such a particular breakup? So consider a density matrix of this form, right? And there is a subscript here, which of a particular sector we are looking at, so particular superselection sector labeled by the electric field configuration. And in particular, the Hilbert space, in this particular configuration, we can take the reduced density matrix. So given a particular electric field configuration, we take the reduced density matrix. And the full density matrix is the sum over the superselection sectors, sum over the PE, where probability of a given electric field configuration. Then we form the reduced density matrix over the sum. So we just carry out this thing. We form the reduced density matrix over the sum here. So where the PE is there. And evaluating the von Neumann formula, we have this particular term. We have this particular expression in which this contribution is the contribution which I call as the contribution from the edge modes. This is basically the probability or the entanglement due to the superselection sectors, due to the fact that there are superselection sectors. So it is this particular contribution which I call the contribution of the edge modes. Maybe there are various things in the literature, but this is what I am calling as the contribution of the edge modes. Now, so it is this entropy of the superselection sectors which we wish to study for both electric and the gravitational field. Okay, and the second term is the usual entanglement of entropy of a region. Now, let me just summarize before we present the calculation. So what we do is we evaluate this particular edge mode contribution for a U1 theory in arbitrary d dimensions. Now, and when we evaluate it, we look for the logarithmic divergence term, which is sort of RG invariant. And we show that we see that it agrees with something called the edge Harishchandra character of U1 field on SD. Okay, SD. So if you're in d dimensions, it's SD. But the sphere is in a d, the entanglement sphere is in a d minus 2 dimensions. And we repeat the same calculation for the graviton in d equals 4. And here too we observe that the contribution of the logarithmic divergence agrees with this Harishchandra character of spin 2 partition function in S4. And also the bulk mode is done, but I wouldn't emphasize that much, but I will talk about the bulk contributions of the entanglement. So let me just outline the U1 theory. So this is the formula as we saw. The edge is sum over PE log PE. And we will work with a spherical entangling surface. And what is this E? This is the electric field configuration on the boundary, as I showed in a little picture. And this of a particular, you choose a particular region and there is an electric field configurations on the sphere. And what is this PE? It's a probability distribution of this radial labeling the superselection sectors. The U1 theory is free. So the probability distribution has to be a Gaussian, whose standard deviation has to be the 2-point functions of the electric field on the sphere. So this is the answer. So P of E is a Gaussian, and if you take, for instance, the 2-point function, it will give you the radial, the 2-point function of the electric field on the sphere. So this is the P of E, and G of R is this 2-point function of the radial component of the electric field on the sphere, and N is the normalization. And if you substitute that in this particular formula for the edge modes, you get this, you just work out the algebra. So the logarithmic coefficient is basically half log the determinant of GRR. So, GRR is this particular correlator, and if you evaluate the half log determinant, evaluate the log coefficient, you should be able to get the edge contribution. Now, so the strategy is straightforward. So you quantize this theory, evaluate its 2-point function, and obtain its determinant, okay, and extract the log coefficient of this. So, and that will be a cutoff, log coefficient with respect to the cutoff. So, so for the Maxwell's theory, the natural variable to do it is basically the harmonic. In the radial, you quantize the thing in vector harmonics. You can go ahead. We expand this in vector harmonics and fix a gauge. This is basically the tangential directions to be set to 0. You can eliminate one. Again, as expected, there will be 2 degrees of freedom after gauge fixing, AR and AM. And if you solve the wave equations, you can actually get this particular expansion. This is a similar expansion as you do in flat space, except that these are all just done in radial coordinates and so on, and therefore the Bessel functions appear. It's a very similar expansion. And then go through the algebra, canonically quantize it, and find the electric field operator on the sphere. It is related to the momentum, and then evaluate its 2-point function. Okay, it can be done once you do this quantization. It can be done, and if you do evaluate this, you can get it diagonal in the momentum in the angular momentum basis. So that's the expression. Okay, so we need to evaluate the determinant of this operator. So writing this correlator in the vector harmonics is technically, though it's complicated, but it results in the simplification that the 2-point function is diagonal in the vector harmonics. And here is the answer. In the harmonics, the diagonal elements are these. And you just have to evaluate the determinant of this operator. And here it is. So it's basically 2L plus 1 into log of L into L plus 1. You can see, yeah. So you can see that that's the structure which comes in, and the degeneracy is 2L plus 1. So that's the way it is. And by looking at it, you see that the the determinant of this edge mode contribution, or the entropy of the edge mode contribution, is basically determinant of a scalar Laplacian. And that's the one here. So one of the things about that scalar Laplacian is that you can rewrite this using a set of identities in the following form. Okay, this is just rewriting the whole scalar Laplacian in a set of identities, and you result in this particular form. And the logarithmic divergence can be extracted by just looking at the 1/t term in this integrand. And that's 1/3 of this. So this rewriting is quite useful because, as you will see later on, this is what leads to the relations with Harishchandra characters. So this is a set of identities involved in rewriting it, and you wind up with this particular form for this for the U1 theory in 4 dimensions. Now, this method of evaluation of edge modes have been carried out by several groups actually. We have just done it in the spherical coordinates, okay, for generalization to the graviton. And we have modified the method actually originally developed by Sawhney and Trivedi, who worked actually in Cartesian coordinates. And we worked in polar coordinates in this manner. It leads to a simplification which helps us to generalize for the graviton. And they worked in the Coulomb gauge, more appropriate for the Cartesian coordinates, and performed a spherical wave decomposition towards the end to bring it in diagonal form, the 2 correlator. And their result is this. Actually, it's a little longish result. We had this in the nice, in a compact form in terms of the Legendre polynomial, in terms of the second kind. So they have it in this particular expansion. And of course, the results we have agreed term by term with this, just as a cross check. So we compared, and they do agree. But let's just complete this. So what we did was we evaluated the edge mode. We can go ahead and evaluate the other term also. And together, this coefficients of the edge together with the bulk, okay, these are the history of various evaluations of the edge mode and the bulk term. And together, initially it was evaluated by Cassini and Huerta, and we had a different method of evaluating it. But together, together when you add the coefficients together, they become the A-type conformal anomaly. Now, this approach of quantizing it in this spherical way, expanding it in terms of vector harmonics can be, of course, carried out to U1 theory in d dimensions. And using this, we notice the general phenomena. So this logarithmic coefficients of the edge mode, in fact, is related to this determinant of a scalar Laplacian on that sphere. Okay, and this is true for the higher dimension, Maxwell's theory in higher dimensions. We notice this by the explicit computation, and you can rewrite it in terms of this Harishchandra character. Okay, so it's in fact just a partition function. It's a transform of this Harishchandra character, and the log term can be easily extracted by it. Now, another observation is the following. Is that if you look at the U1 theory on the sphere, on the full sphere, SD sphere, and you look at its partition function. So this is the U1 determinant, right? It's a partition function of the U1 theory in an SD. When you rewrite it in terms of Harishchandra characters, okay, Harishchandra characters is basically trace over a particular karta. Okay, so if you rewrite it in terms of that, there is two factors to it. One which we can clearly define, identify it as a bulk, and one we can clearly look at it as the edge. Okay, so here it is. Here the first term is the bulk, and the next term is the edge. And if you do this and you keep looking at the edge, right, and the bulk also actually agrees. The edge, the coefficient of the log of the edge agrees with the explicit calculation of the entanglement entropy. So just to identify the edge contribution, one can actually just look at the U1 theory on the full sphere and rewrite it in terms of the Harishchandra character and identify the edge. Okay. That's an observation. We don't know why it's happening, but that's an observation. With this observation, let's move to the gravitons. So the gravitons are basically, we are looking at linearized theory of gravitons. It admits this gauge symmetry. And Riemann curvature is the gauge invariant. And the equations of motion, of course, are the Einstein's equations, linearized Einstein's equations. And in case of the Maxwell theory, the Gauss law resulted in superselection sectors. Now, to obtain a gauge invariant characterization of the superselection sectors in gravity, we think of the Riemann curvature as a field strength in U1 of a U1 gauge potentials. So that's sort of known. So if you construct this particular combination, it's a combination of Christoffel connections actually. If you construct this particular connection, you see that alpha beta is like a label, and this object transforms like a U1 vector potential under that transformation. Okay, and the curvature is basically like the field strength of that U1 potential. Now, the Hamiltonian constraints of gravity is the following. And this, together with Bianchi identity, admits a Gauss law-like description, right? So this is like the Gauss law-like description that we saw in the U1 theory. So the curvature components are analogous to the U1 field, which is what we expected, and the Hamiltonian constraints become Gauss law constraints on that, on that curvature field. So therefore, the superselection sectors are basically, so let me just look at that, show that again. So here is the Gauss law constraints, and the superselection sectors are basically, the fields which are of these, which are kept, same outside and inside that particular region. So these are the superselection sector. They're labeled by 6 components, and the strategy is similar. We follow the same strategy. So gauge fix and quantize the theory using metric fluctuations of tensor harmonics. Determine the relation between the 6 components and the gauge fixed operators which you use to quantize the theory. Like you remember we wrote the F field strength, electric field strength in terms of the momentum. And here it is, electric field strength in terms of momentum. And how much of these are local? In this case, we have to look for that because there it turned out to be local. So we find the, which are the local relations between the curvature, which the Gauss law makes you constant, and relates it to the quantization variable, and then evaluate the 2-point functions. So so we break up the spin field, the spin 2 field into this various modes, basically the vector mode, tensor mode, and the scalar mode. So there are various modes, and you can actually gauge fix it. And finally, again, there are only 2 degrees of freedom. So we follow a gauge fixing procedure developed by Cassini and Benedetti. And so there are finally 2 modes which correspond to the tensor modes, which are, and we can, solve for the equations of motion. And here is the sort of similar to that U1 field expansion in terms of the radial coordinates, in terms of the Bessel functions and so on. So there is a similar expansion which you can do. So you quantize this in tensor harmonics and find the canonical commutation relations. And before we find the correlator, we need to find out which of the 6 components determined by the Gauss law are locally related to the gauge fixed modes. And we do that. So here is the relations between the various these are the variables we quantized, and these are the 2 local relations, and the rest are all non-local, which generate non-local algebras. So we look at these 2 relations, all of them are, so the remaining 4 components are non-local. So we look at these 2 particular curvature components, which are related to the variables we use to quantize the theory, and we evaluate its 2-point functions on the sphere. And again, we can rewrite this 2-point functions in a neat way in terms of that special Legendre polynomials of the second kind, of the functions of the second kind. And there is this particular structure of the terms here. There it was L into L plus 1. Here there is this particular structure. And if you go ahead and evaluate the edge modes, we get this this particular formula. Okay, and we can evaluate using heat kernel techniques, and we get 16/3 log of R by epsilon. We get a coefficient number. Now, how do you know whether it is okay or not? What we do is we looked, because we saw that pattern of the partition functions on the sphere, we looked at spin 2 partition functions on the sphere. And then, we write it in terms of Harishchandra characters. And when you do that, there is this bulk part and the edge part. And here are these expressions. And if you look at the log coefficients from the edge part, it is indeed 16/3, and it agrees with that explicit direct calculation. Okay, this is sort of handle we have on this particular calculation. And for completeness, let me present the bulk part of the entanglement entropy. And it was initially done by these authors. And later on, I think we did it using a different method, and we both agree. And together, they become this. But for this particular case, there is no understanding whether this is the anomaly, Euler type anomaly or not. But this is a contribution of both of them together. In the U1 case, there's an understanding when you put both of them together that it is a A-type anomaly. And for arbitrary spin, using all these connections, we have a formula, but we don't have this direct calculation in terms of this correlators on that sphere. But there is an expression for all of them. So I talked about this graviton, and of course there is, as we saw in the initial discussion, there is this issues dealing with gravitons, partitioning a particular space and understanding entanglement entropy. But we go ahead, we sort of understand, we try to understand whether we can study excited states of gravitons. Okay, that was the vacuum, just understanding the vacuum entanglement. Whether we can actually create excitations in the quantum field theory using graviton, and then study its change in entanglement entropy. Now, so the theory has gravitons, right? Huh? Non-interacting gravitons, free gravitons. So that was the sort of vacuum contribution, which sort of is consistent with other calculations also. And now we sort of try to excite that with a local operator. So this is the local operator O. This is a standard way of creating a quench here. Local operator. The excitation is carried out. So just having a picture in mind. So there is this Y. This is the Y. Y, and then this is Y. xz is here, and then we create an excitation at, say, y0, and let it evolve. So let it evolve. So it evolves like a spherical wave, right? It evolves like a spherical wave and goes into this particular region and asks the question, how does the entanglement jump? We asked that question, and that's calculable, actually, using replica tricks and so on. It's calculable. So this is a surface of, y is xz plane here. So there is an SO2 times SO2 symmetry. And we study the time evolution of this particular disturbance coming inside and increasing the entanglement. And in particular, we wanted to study for the graviton because it has been studied for the spin 0 and spin 1. We wanted to study for the graviton because we want to see how different it is, because there's like all sorts of discussions in the literature that it's very different. But we go ahead. So the nature of the excitations can be probed by evaluating the stress tensor of that density matrix for the spin 0 and 1, but spin 2 does not admit a stress tensor, so we sort of local, gauge invariant stress tensor. So we evaluated the Kreshman scalar in that density matrix, and here is the Kreshman scalar. Just to see the picture, so this is the excitations at t is equal to 0. So there is the spike, and this at higher t it spreads out. This is one particular time, and this is a later time. The amplitude dies, and it spreads out. And, of course, it goes into this half region. Okay. And so you can evaluate the entanglement change. And what is interesting is that you can organize the entanglement change in terms of polynomials, 2s+1 order polynomials, polynomials with, in terms of y and t. So that's the only variable you have, the y and the time at which it hits. So you can organize it in terms of those polynomials. And they can be, for each field which has some particular representations, there is a very nice polynomial structure. And we evaluated this time-dependent growth for all these components of the gravitons, as well as gauge fields. We repeated the analysis. So here is some of the nice.
You have 10 minutes.
10 minutes. Oh, I went through very fast. Okay. So we have this particular case. We can come back to the discussion. So we have this polynomials for each of those fields. And here are some plots. Okay. So once the disturbance enters this region, the entanglement jumps, and it jumps and saturates at log 2. All of them, it saturates at log 2, the various fields. And you can organize them into, as I said, into polynomials of that y by t. And there are 2s+1 order polynomials for the spin s. Okay. And it saturates at log 2. And there is different rates at which it saturates, which can be understood again in terms of the SO2 times SO2 representations. And the graviton is no different. I mean, in terms of at least the linearized theory, it's no different in this treatment. Here is for all the components of the graviton and the various sort of jumps. So let me just summarize. Of gauge theories, especially of gravitons, is interesting. And it's important to understand them more, because it plays a role in holography. And of course, there is all this, debates whether you can actually split a region and so on. Because of this relevance of this particular formula, which is quite important in the recent discussions of information loss, it's important to, check whether these edge modes or how exactly this definition of S bulk plays a role. Okay? And as we saw, the growth of entanglement is controlled by this simple 2s+1 order polynomials in this case. Okay, I will stop at this. Yeah.
Yeah.
Yes.
Can I? Actually, I have a whole number of comments, questions, whatever.
Yeah, it's okay. I know this topic is very interesting.
I mean, the first statement is going back to what was discussed earlier. Even for a scalar field, as far as I know, the Hilbert space does not factorize. You can relate it to type 3-1 nature of the Von-Neumann algebra, goes back to Riesz-Leiter theorem, whatever.
Right.
So what you're saying really is that there is an additional problem from gauge fixing.
Right.
Okay. Now, secondly, coming to the gauge fixing, there are two issues. One is there is a term that arises, so the so-called contact term,
Yeah,
which
this is related to this. Yeah.
this is related.
Yeah.
So that's, I just want to point out that
Yeah.
that was actually evaluated already in 1994.
Yeah, by Kabat. Yeah.
By Kabat.
Kabat. Yeah, these are related. There's the same term. It's the same
Okay.
term. Yeah. In
the-
U1 theory.
In the U1
One
theory.
theory. Yeah.
Yes. Now, if you look at the operator that enters your correlator of the electric fields on the surface, that's also called the Dirichlet-Neumann operator for the Laplace operator.
That I don't know. Okay. Yeah.
Another comment is that when you look at factorization of determinants of Laplacians, there is a formula due to Berleyer, Friedlander, and Kepler,
Okay.
which tells you what is the obstruction to the factorization. And the extra surface term that appears in the formula is exactly this term that you're calculating.
Okay.
So there are many, many factors that come together in this.
Yeah. So we don't understand why that it becomes this Harishchandra character.
I think that's very, very clear if you look at the BFK formula, actually.
Okay.
Yeah.
But has that been done for the graviton also?
No, I'm not talking the graviton.
It's just for the U1.
It's just the U1 case. Anyway, finally, in 2+1 dimensions,
Yeah.
you can actually do this even for the non-abelian theory.
Oh, okay.
Okay, and the U1, where it's much clearer how the factorization occurs. So that's something perhaps we can talk privately. Just want to make a bunch of comments.
Yeah, so hi Justin. So my question is related to what Parmeshwan asked. So the contact term of Kabat,
Yeah.
I thought that is this problem that the ghost mode contributions were not incled and Donnelly and Wall showed that there's a reduction in
So
the...
actually, this is all after that correction.
Okay.
This is all after the correction of that. I agrees with Donnelly and.
I see.
Yeah.
But then how does the Harishchandra side know that ghost has to be, I mean, is there understanding?
No, the
of-
Harishchandra character.
Because they-
So when you evaluate the U1 field,
Yeah.
U1 field on the sphere, you have to do the ghosts also.
On the
Because
S2 you mean?
On the S, on the sphere. Like the Harishchandra
on-
character, by the way, is S4. You
But
look
there
at-
also the ghost is there,
Yeah.
right?
So so you look at S4 partition functions, and then when you write it in terms of these characters, there is this
So you
term.
can see the subtraction of the
Yeah,
ghost.
yeah.
Okay, thank you.
The question that I had is that if the sphere were sufficiently large, then you can look at what happens for a moving charge, right? Because the charge will be inside the sphere for a fairly long enough time for you to do the calculation, let's say, right? So even if the charge is moving at constant velocity, which for example is allowed for the charge to move, would you be able to? I imagine that in that case the PAs that you have will get
So this
recalculated.
Yeah, we don't have like in this theories we are not including matter. So it's just
so what is the when?
So it's just pure, pure vacuum
yeah.
of just
Pure, there's
no matter. It's
okay,
just,
so maybe I misunderstood you right from the start. What is the electric field that is there on the
it's
surface
just the
of the sphere?
configurations. Yeah. It's just
Is that a charge that is inside?
No.
There's nothing inside.
nothing inside.
Okay.
Yeah, edge mode. Yeah.
Just okay.
So far as I can understand, you have not included, this is linearized gravity.
Linear as gravity. Yeah.
So there is no diffeomorphism invariance.
not the full.
So
yeah.
it is simply a spin to massless particle.
Right. Yeah.
There is also already a paper by Brunetti, Longo and Guido and Longo
Okay.
that the moment you give the Wigner representation,
Yeah.
then the localized Weil algebra can be written and the entire localized algebra can be constructed. And they show how the Lorentz group moves it from region to region and what happens when two of them cross. So causal diamond you can go. They have done it completely. And the typology is again type 3-1. Okay, it doesn't matter.
Okay.
The type 3-1 character of these things is because it is like symmetry of all theories of a particular character.
Okay.
So it is true of all quantum field, local causal quantum field theories obeying the Hawk-Castle axioms. So, and what I want to say is, it is not clear to me how this calculation is encompassed in that. For example, today's Longo paper,
I didn't
he
see that.
gets a finite entropy. Okay.
Okay.
And that is because of the split property, which there is a long literature.
So, I mean, let me understand my words. So, this paper, which the logo paper, Longo paper, you see, is that for linearized gravity, it is similar to other quantum field theories. Is that all?
They have actually quantized all Wigner representations
Yeah.
because of the existence of Hilbert space.
Okay.
That's it. Okay. Once you give the Hilbert space, they can write down the localized Weil algebra, which is all bounded operators, and they are of a universal character, and they can construct. Then they move it by
right.
the Lorenz group, which is an outer automorphism. Then they do the calculations, and that's a very beautiful.
They have done similar calculations. I can compare the results with that. I mean,
Today's paper is doing something else.
Okay.
The point is, if you have a causal diamond and you take the causal complement, it can touch at the edge. If there is a touching and you try to compute the relative entropy using Tomita Takesaki modular operator, relative modular operator, it diverges. Okay? There is a universal divergence depending on the, because of the point of contact, and there is also a universal property if you split it a little bit, epsilon distance.
Okay.
So then you have a logarithmic divergence which is universal. Okay?
Universal.
And today's paper, from what this is, I have only.
Do they compute the coefficient?
They find the coefficient which is
Okay.
universal, and they calculate it, and they clarify what the situation is.
So if they have the number, I can compare against it.
I think there is a number. I don't know.
Okay.
Then there is this business of DS. Some
DS.
people have been talking.
DS.
I should say I'm discombobulated. It has horizons. Okay?
DS.
Observer horizons. So it is not at all trivial to make a quantum field theory on that. And this paper of Ed Witten, again Roberto Longo and Chandrasekharan, addresses this issue. So they take one Rilder wedge or the digital space and a complement, and they try to ask, can I trace out the complement as an observer which you are missing? Okay? And they change the type 3-1 by introducing new operators, then it becomes type 2-1. Type 2-1 has an entropy, okay? But it has no minimum entropy. It has a density matrix, but there is no minimum one. There is a maximum one with a maximum entropy. That is unique. So they calculate it and say that it is the same as the Hawking-Gibbons entropy. That is what that
That's the
paper
black
says.
hole entropy.
So none of them uses this technology.
Okay.
Just one last comment, then I stop. It is not clear to me what is meant by restricting a field on an edge. For example, if I take, let's say, smooth functions on a sphere.
Right.
Take all, it is a Caesar algebra. Okay? I want to restrict it on the horizon, on the equator. Can I do it? Is it a subalgebra of the original one? It is not. Because you need delta functions.
Need delta functions.
So what normally is done is this Koszul decomposition. So you take all algebra of all functions, take the functions vanishing at the equator and quotient it. Then you get an equivalence class. That's a set. It's not what is a set. So you get some cohomology, Koszul cohomology. This is a BRST cohomology. You get them. So since you started talking, the only way to transfer it to quantum fields, which are distributions, is to smear with test functions, which are on the whole sphere. Take those which are defined on the equator and smear them and see if you can quotient it. But I don't know whether you can quotient it because it has to be two-sided ideal. So that I don't know. Okay? Because you were raising this, I don't know what to do. Okay? So it is not very clear to me what is happening here. And also gauge fixing. This gauge fixing, just a large comment, is coming because already Weinberg shows that for photons, this gauge transformation is coming because of a lack of an intertwiner between the Wigner representation and quantum fields. Okay? And that leads to indefinite metric spaces. So recent papers, the latest one I know is Mundrer and Schroer, construct what they call string localized fields. Okay? And they are acting entirely on a Hilbert space. There is no indefinite metric space at all. Okay? There is no gauge fixing. So what happens is that these fields get defined on a d-theta cone from a point. Okay.
Okay.
You take all space-like directions from a point, and they write Bessel lines, and then they make completely gauge-independent operators using this. Then what happens is, to me, very astonishing. You get uncountably many supersession sectors. And, huh? Yeah, I'll stop.
Okay.
So let's thank the speaker again. And there are a couple of announcements before.